Okay, so welcome back to our chemistry channel, Teaching Chemistry 30. Today we're going to look at redox stoich. Anytime we're doing stoichiometry, we need a balanced chemical equation. So that's not a difference here. What is a difference is that it has to be a redox equation. So we don't want to go straight into looking at what's reacting and coming up with a balanced chemical equation. We have to see what's reacting and what would be your strongest oxidizing agent, strongest reducing agent, and then get your half reactions, balance electrons, because that is redox is, it's an exchange of electrons, and then from there we'll get that molar ratio. So there's a little bit more work to this, but we'll be able to get there. So as mentioned, what we need to do first is see what's reacting, find all of your oxidizing agents, all of your reducing agents, and then from there you'll pick your strongest OA, your strongest RA, because that's what will react together. Then we'll come up with those half reactions, balance electrons, get our total equation, and then the stoich part. You calculate the problem. So our first question here, here we go, almost, come on. So the first question that we're going to take a look at is this one here. Maybe I'll just leave it here for a moment. So we have a solution of potassium permanganate, and we're going to use to analyze an acidified solution of tin 2 chloride. So even before I look at my problem, what I can look at is what's reacting. So I guess I do need to put it back in presentation mode here to get the pen to work. I'm really sorry. So here we go. So when we're looking at what's reacting, we want to split up what we can. So you can split up ionic compounds in solution. So you have potassium permanganate, which would be the potassium ion coming together with MnO4. And then you would also have, if it's acidified solution, we have acidified means you're going to add in hydrogen ions, and anything in solution means water is present. And then lastly, you have tin 2 chloride, which is an ionic compound, and you can break it up into its ions. So once we have that, then together we would look at your data booklet, and I'll take a look at it on the next page in a moment. But from your data booklet, it's organized with your half reactions. For OAs on the left, RAs are on the right, and it goes strongest to weakest for OAs, and from the bottom on the RA side, it goes strongest and up towards weakest. So once we look at all of our OAs, so we go through the chart, we would see that potassium is an OA, MnO4 with hydrogen is an OA, water is an OA and an RA. The tin 2 positive, that's on both sides of the chart, so OA and an RA, and the chlorine ion is an RA. Then to see what's the strongest, again, now we're looking at the data booklet and we want to see which OA we're going to see first. And from the top of the chart, 3 down, you'll see that your permanganate with hydrogen is your strongest OA, and the tin ion 2 positive is your strongest RA. So we can get our half reactions. So with your strongest oxidizing agent, it undergoes reduction, and your table is reduction half reactions. So we can write down this half reaction exactly how we see it. So MnO4 negative plus the hydrogen ion, and it's 16 hydrogen ions, plus, oh, sorry, I skipped a step. It's 8. I was going straight to my balanced equation. So it was 8 hydrogen ions plus 5 electrons, and it would give you Mn2 positive and 4 water molecules. So that's our first reaction, or half reaction. The second half reaction is with tin 2 positive. So you will be looking on the RA side, and because reducing agents undergo oxidation, you want to write this reaction down backwards. So we would see that the tin 2 positive is reacting, and you would have SN4 positive and 2 electrons. So again, we're flipping this reaction so that we can make tin 2 positive undergo oxidation, and we also know it's a reactant, so we want to see it as a reactant. Then now that we have our 2 half reactions, we can balance our half reactions by balancing electrons. So multiply that first reaction by 2 and that second reaction by 5. So that would mean 2 times 5 is 10 electrons, 5 times 2 is 10 electrons. Your electrons would cancel on each side, and we can come up with our net equation. So we'll have, I'll just write that all down, 2MnO4 negative, and I should be writing the states, but just to save time, I will just write this out. So we're writing down all our reactants. So our reactants from the first half reaction, once we distribute that 2 through, and then from the second half reaction. So 5SN2 positive. And then we write down all our products. So we'll have 2Mn2 positive plus 8 water molecules, again, distributing that 2 all the way through. And then when we look at the second half reaction, for your products, you would have 5SN4 positive, and then those 10 electrons. But your electrons would cancel on each side. You'd also cancel out anything else that you can, and we can't cancel anything else, so we can go straight to the equation. So from here, now that you have a balanced chemical equation, you can apply the stoich. So when I'm reading up here, I have my volume and my concentration of the potassium permanganate, which would relate to the MnO4. So I would have, if I change that into liters, 0.0143 liters, and I'd multiply that by the concentration. And this is of your MnO4 negative, so moles per liter. So this first step, liters cancel. Now I have my mole ratio, and I want to turn my moles of my known into the moles of the unknown, which is asking about the tin ions. So that's a 2 to 5 ratio. If I want the MnO4 to cancel, I need to put the 2 moles of MnO4 in the denominator, and then the 5 moles of SN2 positive in the numerator. So now we see the moles of MnO4 cancel. And lastly, because it is concentration, when you're done, you want your units to be moles per liter. So we know the volume of the tin 2 chloride, so we could take that as the volume of the tin. So 0.025 liters in the denominator. And then from our equation, we would want 2 significant digits. And so here the concentration, once you plug that all into your calculator, would be 0.0046 moles per liter of the tin 2 positive. So sorry, I know that gets a little bit squished, but that is our process. So list all your OAs, your RAs, figure out what's strongest, come up with your half reactions, balance electrons, add your 2 half reactions together, and then apply the stoich. So that was our equation. Just in terms of our data booklet, this is the one I'm referring to. So this is from Chem 30. This is the data booklet the government gives out, and in Alberta. So when I'm looking at, when I was talking about the table of the OA and the RAs, when you're looking at your table, that from this arrow is what would split the table up. The OAs are on the left, the RAs are on the right, and then you go strongest to weakest for your OAs, and then strongest going up to weakest for your RAs. So when I looked at my previous example, that's why my strongest OA was MnO4 negative with the 8 hydrogen ions. Even though we had some more OAs listed, that's when you see first. So that's what's going to react. And then on the other side, starting from the bottom, you want to read up the chart, and then you'd see the tin 2 ion listed first. And then again, because this table is all reduction, the oxidizing agent that undergoes reduction, you could keep that just as you see it. But the reducing agent, which would undergo oxidation, that means you need to flip this reaction to use it. So that's how we got our 2 half reactions, and then we added them together once we balanced our electrons. Now, one more example we could do is if you had a solid and you're applying it or mixing it with hydrochloric acid. So again, don't be tempted here to do just a single replacement reaction. We can't do that because it is a redox equation. So we're going to start in the same way. We're going to see what's reacting. So you have your silver metal, and it's lowered into a solution of hydrochloric acid. So it does tell you it's a strong acid here, but you could take a look at your data booklet and find that out as well. And why that matters is strong acids will split into their ions. And then if you do have a solution, we also know that it will have water present. So now you would go through your booklet, and just like we did on the previous example, you want to figure out what are your OAs, what are your RAs. And you'll see that your hydrogen ion is your strongest oxidizing agent, and your silver solid is your strongest reducing agent. So I would take a look at my data booklet and I would write down these reactions how I would see it. So my half reaction for the hydrogen ion undergoing reduction is 2 hydrogen ions in solution, so an aqueous state, plus 2 electrons to give you hydrogen gas. And this is good that we're seeing that because it is asking how much hydrogen gas is produced. So you do want to see hydrogen gas as a product. And then when you take a look at your RAs, you would see that silver is your strongest. So again, we're going to flip that half reaction. So you have silver, and that would be giving you Ag positive plus an electron once it underwent oxidation. Now to add these two together, I need to balance my electrons. So I just need to multiply the second equation by 2. And so then I'll bring it down here. My total, or my balanced chemical redox equation, will be 2 hydrogen ions plus 2 silver metal pieces to give you hydrogen gas, which we're looking for, plus 2 silver ions, and your electrons would have canceled out once you multiplied by 2. So once we have this set up, and if you like, we can add in states. I often skip the states when I'm showing my work, or not showing my work, sorry, just to be faster. But now that we have this, now we can figure out what we have. So we have our known silver, 20 grams. And if you have 20 grams of silver, you can always turn it into moles by using the molar mass of silver, which was 107.87, and you're just getting that from your data booklet. Then once you have moles of silver, we want to figure out the moles of hydrogen. So now you're using your mole ratio. So we'll multiply this by 1 mole of H2 on the top and 2 moles of silver on the bottom. And then lastly, because it's asking for mass, when you're done, you want grams. So your last step is to get moles to cancel and be left with grams. And we can do that with the molar mass of hydrogen, which is 2.02. And so that would be for 1 mole of hydrogen. And you would be able to see all your units canceling. And when you're done, you're left with the grams of hydrogen. Now, our sig digs, we have 2, so we would want to keep 2 sig digs, and my key is a little bit messy here, but I believe it says 0.187, so we'll round that 8 to a 9, so 0.19 grams of hydrogen gas would be produced. So that would be our answer. So I hope this lesson was helpful for you. Remember your steps. If it is a redox equation, you'll need to figure out your strongest OA, react it with your strongest RA. Before you add your half reactions together, balance those electrons, and then do your stoichiometry like you would have in Science 10 and Chem 20 to get your answer. I hope this helps, and have a good day.